Before the introduction, my name is Hayashi, belong to Hiroshima University. I'd like to talk about fatigue design recommendations for anodized aluminum alloys A6061. First, let me talk about background of our study. In recent years, global warming issue had attracting attention all over the world, and the automotive industry is required to reduce the weight of automobiles to achieve carbon neutrality. So the demand for aluminum alloys, which are light metal materials, is increasing, and the percentage of aluminum alloy used in automobiles is also increasing year by year, as shown in light figures. Aluminum alloy has many advantages, such as the low price, high portability, and easily recyclable. However, since the surface is easily scratched and corroded, so many products are treated with surface treatment. In this study, we focused on the anodizing treatment. It is an electrochemical process that converts the metal surface into a decorative, durable, corrosion-resistant, and zinc oxide finish. Generally, it is known that the anodizing treatment decreases fatigue strength, but this is mostly the result of rotating bending or flame bending. So there are few reports on fatigue properties under axial load. Moreover, it is not illustrate the fatigue fracture mechanism of anodized aluminum alloy in detail. So aim of our study is to investigate the effect of anodizing on fatigue properties under axial loading. Next, let me talk about specimen used in this study. We used A6061, which is T6 treated. Its chemical composition and mechanical property are shown here. The schematic diagram shows the shape of a specimen, and the polishing shown in the next slide is performed under these conditions before anodizing. We prepared three types of specimen. Solution heat treatment and aging treatment are performed on round ball. The round ball was machined into specimen shape, and our section was polished. Hereafter, we will be referred to as virgin. Next, two types of anodizing specimen. The thickness of 7 micrometers and 20 micrometers were prepared. These specimens were referred to as AN7 and AN20. Moreover, this is the close section that was polished and observed by SEM. As a result, the AN7 and the AN20 are forming the target film thickness. Today, I will present the effect of anodized film on fatigue strength compared with virgin in the AN7, and the effect of anodized thickness on fatigue strength compared with AN7 and the AN20. This is the surface observation result. The A2C shows the result of surface observation on each specimen. As a result, the virgin and AN7 weren't observed cracking, but AN20 was observed cracking to the surface. Crackings were observed to occur randomly, especially in the horizontal direction of the load axis. When the cracking was observed in the direction of anodized film, as shown in D and E, it was found that the cracking did not propagate the base metal. So moreover, the pit were observed in the direction of anodized film, regardless of film thickness. This is the static tensor test result. The test condition is shown here. and the vertical and the horizontal axis applied stress and strain, respectively. As a result, berthing in 7 and in 20 has tensile strength of 380 megapascal, 368 megapascal, and 382 megapascal. So anodizing treatment hardly affects tensile strength. Next, it is known that the anodized film is composed of almost amorphous alumina, and clotting can easily occur. The anodized film affects not only corrosion and wear resistance, but also fatigue strength. So we investigate the critical stores at which cracking occurs. As shown in upper right, the AN7 is subjected to the tensile stress of 40 megapascal, and then loaded. And the surface properties of the anodized film is observed by SEM. This operation performed once, and the loading and unloading tests were conducted by increasing the loading stress by 40 megapascal until clotting occurred. As a result, numerous clotting were observed in the direction perpendicular to the load axis at sigma equal to 160 megapascal. So it is defined critical stress in this study. Next, this is the fatigue test result. In this study, axial load fatigue tests were conducted at stress ratio R equal to -1 and the frequency F equal to 20 Hz in room temperature using hydraulic subpulsar. Box circle shows the result of berthing. Red triangle shows the result of AN7, and the triangle shows the result of AN20. First, berthing and AN7 were compared to investigate the effect of anodized film on fatigue strength. As a result, anodized film hardly affects fatigue strength in high and low stress amplitude range. On the other hand, in the blue area, the fatigue line in AN7 showed the variation. This result is consistent with critical stress at which cracking occurred in the anodized film. Next, the AN7 and AN20 were compared to investigate the effect of anodized thickness on fatigue strength. As a result, the fatigue strength decreased with increasing film thickness. This tendency was more significant in the low stress amplitude range. Moreover, the variation in fatigue life observed in AN7 was not confirmed. The AN20 has many clotting. AN20 has many clotting. So the clotting become a source of stress concentration, resulting in decrease in fatigue life. Next, to investigate fatigue fracture mechanism, we observed fracture surface observation on each specimen. These are results of berthing in the AN20. First, regarding berthing, the berthing exhibited the surface origin fatigue fracture, the similar result obtained for all tested specimens. Next, regarding the AN20, the step shapes were observed on side view, and it was confirmed that the cracks were occurred from step shapes. Since step shapes is linear, it is assumed to be the brittle clotting, and is considered to be cracking of anodized film. Next, this is the result of AN7. AN7 exhibited different fracture morphology above and below the critical stress. The upper figure shows the result of sigma A equal to 220 megapascal, which is high stress amplitude length. As a result, step shapes were observed similar to that of AN20. So the fatigue fracture exhibited with each cracking on the fatigue crack initiation point. Next, this is the result of sigma A equal to 120 megapascal, which is low stress amplitude rate, does not have observed step shapes. So the fracture morphology differs depending on the stress value, with the critical stress value as the boundary. Now, we didn't elucidate the fatigue fracture mechanism using SEM observation. So I conducted fatigue crack propagation observation using the following method. The fatigue test is interrupted at 60% of the number of cycles to the estimated failure life obtained from SN curves of AN7. This specimen is taken out and cut near the anodized film by electrical discharge machining in the direction of load axis, and then filled with resin. Resin-filled specimen was observed, polished and observed by SEM. As a result, in the high stress amplitude length, crack propagated from the clogging are shown in red circles. On the other hand, in low stress amplitude length, the crack initiated and propagated from the interface between anodized film and the base metal. So fatigue fracture mechanism is different between stress amplitude. Finally, this is the conclusion of our study. First, regarding the effect of anodized film on fatigue strength. Under the conditions of stress ratio are equal to -1 and axial loading fatigue test, and the anodized film flagging is a factor that reduces fatigue strength. But if the flagging does not occur, the fatigue strength is not reduced by anodizing. Next, the effect of anodized thickness on fatigue strength. The fatigue strength decreased with increasing film thickness, and a significantly different result was observed in a low stress amplitude range. Finally, the fatigue fracture mechanism of anodizing. When the cracking does not occur, fatigue crack occurs at the interface between the anodized film and the base metal. When cracking occurred, the anodized material exhibited fatigue fracture initiated by clogging. That's all for my presentation before admission.